So thank you, Gunther, and go ahead.
Okay, thank you, everyone. So let's, in here is a group of authors where everyone has its own part. And so I'll go just quickly what we did. We provide a collective evidence best explained by the hypothesis that at least one high energy, high temperature, hypervelocity airburst occurred near Abu Hureyra 12,800 years ago. And so now let's dig what it is. So there is a site in Syria, and there was a dam project. They were making a big dam, and in order to, to excavate the area for any kind of like archaeology, there was this site that was excavated quite intensively in 1972 and 1973. And then afterwards, the area was flooded. But in here, you can see the location of the site. There is 100 meters for scale. And so you can see there are several pits, and the blue pits that are here are where the samples I'll be talking about are coming from. So the age of the culture that was living in this village Abu Hureyra is 12,800 years ago. Now here's the pit from which most of the samples you will see, and so in here you can see with the red arrow is a dwelling where people lived. The orange yellow was the working area. A lot of these, there's a 1 meter for scale down there, and a lot of these holes are different things that people were like digging in order to utilize the surface at the time of living there. Now also notice this orange line, which is the level that have all these like a weird features, and I will be talking about it. There's the occurrence of nanodiamonds, there is occurrence of microspherules, and there is a lot of melt glass. Just melt glass along the, it's about 30% in that layer of melt glass. So, and this is what will be what our analysis were done on. So we did analysis of sedimentary proxies in this layer for abundance peak, morphologies, we did geochemical composition, crystallinity, boiling temperature estimate, carbon reflectance, we did remnant magnetism and water content. And for that we use SEM analysis, reflected microscope, electron microprobe, magnetic sensing, reflectance, and FTIR. So just to give you an idea, if you look on this site, I mean, there's a depth profile, and at very specific depths near 4 meters, you can see there was this abundance of microspherules or spherules, because they are centimeter, millimeter size. They are up to like a 600 per kilogram of this layer sediment. There are nanodiamonds that goes almost up to 450, 500 parts per billion. There's a melt glass, so note there is like a 16 grams per kilogram, and there's a carbon spherules that are also abundant, about 160 per kilogram. So a part of this work was done by heating. We basically took various material from the layer and the adjacent sediment, and we were just heating it up because we are dealing with melts, and we just wanted to know what happened when we melt this material and what kind of phases are appearing in a melt, which are disappearing. And so we were melting this Abu Hureyra sediment, and so we could see that at 1200, 1300, there was a melt formed, and we could see that some of the small quartz grains took part in this melt, because just for, when you have one phase, the temperature of melting is much higher than when you have more phases involved. That's always lower the temperature. That's why you can have a quartz which is introduced into the melt at like a 1200, but there may be also quartz still unmelted at like a 1700, which was also this case where we could see that some quartz were still present at 1700 degrees Celsius. The glass which was forming had like a brown color, and it was very similar to the actually Abu Hureyra glass. And then during the cooling, we saw that there was this like a solidification of the sediment that we melted at 1300. And when we did the same thing with the glass, we just remelted the glass of Abu Hureyra that we found, and then we watch when it becomes solid. It was the same temperature, so it was another like that this is probably happening. The material is the same. Another interesting thing is that there are this this molten pieces you find there. About 40% have like imprinted like organics in it. I don't know, some of you may have been in Hawaii and you've seen like a tree mold. And there's a lava flow coming down the hill. There's a tree, a palm tree, right? The lava goes around it. And now the lava just next to the tree solidifies quickly because it's cooled by this organic. And of course, the tree is burning and evaporating. But as a result of the tree mold. So this is a kind of like a similar way how we think about it. That there was a very like a fine, like a molten material that was just hitting the surface organics and created these molds that are here on this figure shown by P, which is a plant material, and there's Abu Hureyra glass. And so we did also some of the melting and to try to figure out what was the temperature at which this specific mold disappeared, which was about 12 to 1300. Let's look at some of these objects that we see. I mean, there's a lot of glass there. I mean, some of them are almost like a centimeter size, but it's very rarely that you can find like intact, like a glass, like a global. And so in this case, those are some of the few cases where we could find intact, like a glass, complete, was not broken. Most of the time it's broken. And so we can see the optical image on top and the SEM image at the bottom. One thing is that this glass very often had a very weird like minerals in it. There was a chromite, monazite, but I will show that I mean, it's not just presence of the mineral, it's just that those specific minerals, there was evidence of partial melting of these minerals, which gives you a clue what was the temperature of that melt at the time of melting. So here is a lot of this glass is very vesicular. Vesicularity means there's a lot of bubbles. And so if you take this sediment, right, and you drop it into the water, one way you can find these glasses is that a lot of these glasses is just floating because there's a lot of this vesicularity. So you can just see it on the surface of water and you just take it and then you can analyze it. And looking like a closely, I mean, there is an optical image here, and a lot of these internal surfaces of vesicles sometimes have a lining of like an iron oxide. In this case, you can see this reddish color, which is probably in this could be like a hematite or maghemite. And then we have like examples of these SEM images. But what I would like to point it out that once you look at some of the smooth surfaces, very often you can see this kind of lineation or lining that shows that there was actually motion of the fluid at the time of the solidification. And then in some of these vesicles inside, you can see like a crystals, like a coarse crystals growing, probably when the melt was just evaporating, there was a lot of gas, and from the gas you could form crystals. And then also we can see this quench, like a diopside crystal that form on some of these surfaces. About these plants, always when we look at these plants, there was this three-layered imprint morphology. There was a calcium silicate glass, which was fused with a micron-thick silicified plant material, and there was some kind of transition in between. As I said, I always think about this process same as are these tree mold, either in Mount Fuji in Japan or in Hawaii, where the lava flow just go around the organic and create this mold. But this is like a small scale. We find along these fused layered plant imprints very often weird mineralogy and weird composition. We found common associated with nickel, cobalt, iridium, and platinum. I will show some examples of that. So here are some examples of these plant imprinted materials. So we can see the optical images on top. The P is visual indication where is this plant. And then the rest of it is always the Abu Hureyra glass. Then we have SEM images. And once you have a SEM property, ability to do, then you can do composition. And so in this case, you can actually color the different part of the composition. So you can see like aluminum in a purple, then you can see calcium in a blue and silicon in orange in all these 4 images. And so you can see that the aluminum is quite like a aluminum. The purple is mostly the glass texture, which is made, which is enriched. In here, this glass, there's an indication that it was formed in the temperature greater than 1200 degrees C. However, when we found commonly on a broken surfaces, like inside these glass, that there are some charred organics, and then from the reflected imaging, we could estimate that the interior temperature of the glass was only like a 400 Celsius, which means that's like way like a 700, more than 700 degrees Celsius lower temperature was inside than on the outside. Lechitel lyrite. Lechitel lyrite is an interesting thing. It's a glass. It's like a SiO2 glass, but it indicates usually very high temperature. Here we can see like 3 examples of Lechitel lyrite. And it's usually on a surface. I mean, if you, I will think about it as like a space weathering. If you go on the moon, there is the space weathered rock, right? And it usually, because there is this like impact of space weathered material, which create like a local melting and makes a little bit like a glassy surfaces on the surfaces of the moon stuff. And here it's kind of similar, that you can see this Lechitel lyrite is like a blanketing over the surface of the Abu Hureyra glass. In A and B. In a C, you can see that you can see the glass, but there's a quartz grain. This is not the Lechitel lyrite, but it's a quartz grain. But you can see there's a transition, that part of the quartz grain is molten and parts is still present. So these things gives you some idea, because the quartz melting point of quartz is like a 1720. However, when it's in contact with some other material, usually the temperature of that goes down, and the temperature can be lower, like 1520. So we know it's between 1520 to 1720 when this melting occurred. I hear the ding. Thank you. Look at this example. I mean, look at that Lechitel lyrite. If you've never seen it, I mean, it's beautiful. You can see the glassy textures, and you can see this like even pointed surfaces of Lechitel lyrite, which is quite unusual, indicating again like a very high temperature. And in here, the Lechitel lyrite is blanketing these flow marks, which mean that this material was in motion at the time of deposition. And when you look at like a little closer, the Lechitel lyrite has this very interesting morphology that you can see kind of like a, you know, this repetitive pattern. And you can see sometimes like a disturbance of this pattern because of the material which was underneath, that was, for example, had like a different temperature conductivity. So it showed some anomaly. And in here, this is an interesting example where Lechitel lyrite is making this like a perpendicular kind of a pattern versus this fracture in the glass. It's again like some like amazing image that I've never seen. And look at that, melted quartz. I mean, if you look at when you look at the sample, you can see now this blob of something, then you just measure the composition in the middle. Okay, it's quartz, but it's so kind of weird. It doesn't have really good boundaries. But then when you look at when you measure the composition away, then you can see it's like a diffusing away into the glass. So you can see 100% quartz, and it's going less and less until it becomes the same composition as Abu Hureyra glass. And in here, zircon, right? A lot of you may have zirconium fake diamonds, right? So this is zirconium that you can see. And so if you would be in this village and have this zirconium diamond, I mean, it could have melted, because this is actually zirconium, like 100%. And then as soon as you go away from the zirconium, it just, you can see how it's dissolving. So it's evident that the zirconium completely was molten in this Abu Hureyra glass. Here is another evidence. We have this Abu Hureyra glass, and we have the chromite grains. Chromite grains usually you need very high temperature to get the molten chromite grains. So this is a chromite with iron, which means it's probably chromite magnetite grains, and you can see 2 of them like next to each other. And so they were inside the vesicle, on the surface of the vesicle of the Abu Hureyra glass. And when you look into detail, some of the chromite grains were associated with gold. So we found chromite with gold association, again, on the surface of these vesicles on this glass material. And this one, I don't know, when I look first at this image, it kind of reminded me about I hear the Deng about the Palace hair. You know, Palace hair is a kind of a volcanic material, which is kind of like a wind blown, like making these in Hawaii, these long features. So, but this is not Palace hair. This is much smaller, right? And it's actually, if you measure the composition, it's 88% iron and like a 12% chromium, and there's no oxygen. So it's very reduced, right? No oxygen found in this grain. So this is very spectacular, and perhaps the surface was made because of the formation, airborne formation. And one thing, this again reminds me about the space weathering, because when you look at the moon on some of the dust particles, you can find these like a similar kind of feature, these blob of iron on the surfaces as a result of quenching and cooling and creating these spheres of iron. Of course, there you can see there's a different scale. I mean, there's large scale iron blobs, small scale. And if you go smaller, you would even find, I mean, it goes almost to like a micrometer to nanometer scale. And the composition goes from this iron, silicon, magnesium, calcium composition. And this is one of my favorite images that shows like a magnetite, which has evidence of boiling. There's a magnetite, and so there's a titanomagnetite. And they both have a weird morphology that shows that perhaps it was boiling. And then there's evidence of pure iron, like very reduced, and we could see also some iron sulfide and troilite. Troilite is a material which is on the moon, like 1/3 of iron is in troilite on the moon. 2/3 are just like iron or iron oxide or iron nickel. So troilite is very common, like on the moon or a meteorite, but here on Earth, that's uncommon. And this is again like showing that the composition of these iron is very often with nickel, and some of the iron is actually with platinum and iridium, as shown on this picture. So weird composition, and I'll go fast. There's iron silicate composition material, and then I want to like to also look at this troilite, because we found we have a glass from Trinity test. Trinity test was this nuclear explosion in air, and which created pools of glass underneath this nuclear explosion. And so that test on Earth also were able to produce troilite grains, the same like we can find on this Abu Hureyra glass. And this is a monazite. Monazite is again a grain that appeared on this picture. It was molten away in a glass. So many evidence of being melting. Part of the things, because someone could say, oh, there was like a big giant lightning. The lightning bolt can also melt stuff, right? I mean, all the stuff you have, it's just lightning. But if we have evidence, magnetic evidence is not the case, because lightning strike produces fulgurites, and fulgurites magnetically are saturated, meaning your barrel would be full of water, saturated. That's what
Gunther,
fulgurites are. Yes,
we do have several questions for you. If you could wrap it up really quick.
Yeah.
Questions.
And we have a water content that also is very specific for this. It's very dry, and we found evidence of like many minerals that shows like various high temperatures, and from that we were able to recover like a temperature history. We could also show that there was a high reducing conditions, and all of these things, if we put it together, I'll put it in a we think that Abu Hureyra glass must be a result of an impact event because of this increase in the evidence that we found. And the glass has characteristics of glass and tektites, and the collective evidence support that in Abu Hureyra there was maybe an airburst, and because airburst evidence is also in multiple other locations around America and Europe, we think that they may have been like a comet debris, like an encounter with a 1 million kilometer wide debris cluster is 1,000 times more probable than collision with a 100 kilometer wide comet or 10 kilometer asteroid. So this is where we are coming from, and that it's a hypothesis, but we think this our data support this hypothesis.
Great, thank you. All right, let's move on to the couple of questions in our remaining 5 minutes.
Yeah, so I'm going to combine Sean Gulick's second question with Clark Chapman's comment. Sean's second question basically gets to the point of where does the 12.8 thousand years ago date come from? It's rather convenient. And Clark follows that up by saying that the chance of such a huge impact 12,800 years ago is extremely unlikely, like 1 in 100,000, for either of the two younger Dryas onset proposals. And then he lists what those proposals are. He says that these ideas totally ignore what we know about asteroids, comets, and impact physics, and a lightning superbolt could explain much of what you found in the 1970s Syrian samples. So I think both of these really get to the date of 12.8 thousand years ago.
Okay, thank you for this question. Let me start with this. We found this the evidence of this layer of spherules in multiple locations, and one of them is also in Central Europe. And in Central Europe, there's a La Creuset tephra, which is dated precisely by trees. It's 12,820 years before present. And then in a sediment where you have this tephra layer, which we know exactly where it came, about centimeter above that layer, we have this evidence of these microspherules that we think has a similar similar like in this location, Abu Hureyra. And so from that, we can very precisely date this event because it's so close to this tephra event, and we know the sedimentation rate. And so this is one way we deal with that we think we can date it very precisely. So it's just at the beginning of the younger Dryas. Then there was a question about the unreasonable, there's no impact crater. We think that this is, we know, I have also talked about Tunguska. Tunguska, there is no crater, there's level trees, and it's because of the airburst. If you have an airburst, you just have a lot of energy deposited on the surface. In Tunguska until today, we didn't find any evidence that there was some foreign body. We only know there was an airburst. And so that would explain why we don't have like a big giant crater, because this is a different mode. It's not asteroid. It's not like a really like a solid object. It's maybe some very porous ice, which is not capable, to penetrate in the atmosphere because of the density of the atmosphere and density of the impactor. Yes.
Okay, I'll go to Sean's first question. Beyond evidence for higher temperatures, is there any evidence for shock metamorphism?
Good question. We found shock metamorphism means that for example, we would find PDFs in quartz. We have some evidence that there are PDFs in this location. So planar deformation features means that what's interesting about this that it appears that there's usually you have like a multiple sets of PDFs, but in this case it appears that there may be only a single set of PDFs. So there's some indication that there was like a shock pressure that was exposing some of the surface grains at the time of this event.
Okay, I'll go ahead and do the last comment, comment and question from Anya Losiak again. Archaeological analysis showed that similar melt material, including melt droplets, plant molds, and partially melted minerals, are not uncommon in various locations and at various times. Places where these silicate melts were found correlate well with locations where people were building huts made of straw mixed with animal-derived organic material and soil, which burn at very high temperatures. So related to that comment, the question, have you found confirmed existence of those kinds of melting features from places outside of fire-susceptible straw huts? So in other words, okay.
Yeah. Thank you for the question. We found evidence of chromite melting, like over 2,000 degrees C. It's not the temperature of the burning of the hut. When you have grass fire, it's usually 400 degrees C. When you have forest fire, it's usually about 800 C. Could have a forest fire in some very good location. When you have a straw hut, I don't think that you could, by burning the hut and organic, could get the temperature as high. But it's a good question, and you of course there is a lot of complexities like during the burning. But in this case, I think the temperature is a little bit too high.